So actually, this is a continuation of last week's seminar. Last week, as Sanjay said, I had two students talking about age estimation and minding Wikipedia. And today I'll have two different students talk about two different projects. Mert talk about video event detection, and Dennis talk about 3D hand tracking. So the topic of my talk is video processing, the need for speed. And before we get into the technical details, I have to explain about this title, especially a tale of two titles. You know, when Sanjay approached me and Narendra about giving talks in this series, they listed us both for computer vision. So if you look at the list, there's computer vision, there's computer vision. So I said we must have some different title. So I changed mine to video processing. Right? So for a time, you see computer vision, video processing. But when Narendra gave his talk, actually his title is Video Acquisition and Understanding, not computer vision. So what do I do? Well, one possibility is change back to computer vision. But I know what video processing is, but I don't know what computer vision is. So I keep video processing, just add a subtitle. So this is the final title. So as Sanjay said, we have three parts to this talk. So first I'll give 10-15 minutes overview of the things we do, my students and I. And then we have two presentations on two projects. Mert talk about video event detection, and Dennis talk about 3D hand tracking. And the reason for choosing these two is because Mert and Dennis tried some GPU implementation for some of their work. So it'll be interesting to see the comparison. So video processing, there are a number of sub-areas, mainly 4 of them. And we have coding, including compression, transcoding, watermarking, and so forth. Enhancement, especially noise reduction, super resolution, analysis, understanding, and then synthesis. And actually, we have heard a number of excellent talks on these topics, if you recall. So Sam Blackman talked about transcoding, and we had a very interesting talk by Nicola from Motion DSP about noise reduction and super resolution. Actually, he talked about some of the work done by Payman Milanfa, who's supposed to give a DSP seminar today at 3 o'clock. But his plane was delayed by 5 hours, so he couldn't get here. So the seminar was canceled. And the DSP seminar every week, actually, it's supposed to be at 4 o'clock. And this week, because we have this seminar, they moved it to 3, but the payment didn't make it. So this could also serve as the DSP seminar of this week. Okay. Then Narendra talked a lot about various aspects of video processing, including analysis, but also acquisition. And in analysis, he spent quite a bit of time talking about segmentation. And then on synthesis, we had a talk by John Hart talking about, I unfortunately missed his talk, but according to Dennis, he talked about various issues, work on
all these 4 areas, but the main emphasis is actually on analysis. We also do a little bit of synthesis. So what you'll hear today from Mert would be more specifically video event detection, but the 2 aspects for video event detection feature it on. And Dennis will talk about 3D hand tracking and using an analysis by synthesis approach. So it involves rendering, but it's a very special kind of rendering. So the capital letters are the topics you'll hear from Mert and from Dennis. Right. So I talked about this last week at DSP seminar. So those of you who happen to attend that one can fall asleep for 5 minutes. Right? So broadly speaking, we are doing multimodal multimedia signal processing.
Multimodal means in terms of sensing, we are mostly interested in audio and visual signals. Audio, especially speech, of course, but also non-speech sound. And when we say multimedia, we more think in terms of how we represent the information. So there are different ways: audio, images, video, graphics, and text. And of course, we're all working on signal processing. But again, our emphasis at this moment are mainly analysis and understanding. Oops, I'm pushing Mert's computer. So. Okay, now our research is motivated by applications. And right now, there are 4 major applications which drive our research. And these are, I'll say a couple of words about each one. But first is multimodal biometrics. And also, since this is a talk on video processing, I won't say too much, if at all, about audio. But we do a lot of joint audio-visual processing. So, biometrics, then spatial temporal pattern recognition, including object recognition and event recognition. An event involves time. And the 4th area is multimedia indexing, search, and mining. Okay? So just a few words about each one. Biometrics, usually people mean personal identification. And we can call that hard biometrics. But we are also interested in soft biometrics, which is not trying to identify the person, but trying to recognize some of the attributes of the person, like gender, age. For example, Sanjay was what, 15 years old? Okay. And the ethnicity, emotion. And we're interested in all kinds of data types. Now, of course, hard biometrics has many applications, but soft biometrics also have interesting applications. For example, in consumer relationship, like in McDonald's, McDonald's would like to find out how many percentage of male teenagers buy Big Mac. So if you have a camera looking at the customer, and if you can recognize the gender and age, then you can compile statistics. And if you can recognize emotion, you can make your public display for commercials adaptive to the state of the audience. If the audience seems to be happy, you show more of the same. If they are not happy, you change the advertisement. And last week, one of my students, she talked about age estimation. And he actually has a real-time demo. So those of you who are interested can go to him and see how old you are. Okay. Then the second area is spatial temporal pattern recognition. There are 3 kinds of patterns of interest, usually. Objects, people, vehicles, sites, like outdoor or indoor, and action and events, which of course is perhaps the most interesting part, because it depends on temporal cues. And MERT, we participated in a number of evaluations and competitions last year for event recognition, and MERT will tell you about the Tredwick evaluation. Then human-computer interaction, there are 2 directions of communication. From the human to the computer, of course, you would like to command the computer to do things for you. And in addition to the conventional keyboard and mouse, we would like to explore new modalities of interaction through speech and gesture. For example, using gesture and speech to control display. And Dennis will tell you about his work on 3D hand tracking. But there's another aspect of getting information from the user to the computer, and that is, in many applications, the computer, if you're interacting with the computer, like in a computer-aided learning scenario, how the computer responds to the user should depend on the state of the user, the physical state, emotional state, or cognitive state. So if you have a camera looking at the user, and also if there's a voice interface, you analyze the tone of the voice of the user, and you try to assess the state of the user. And if the computer thinks the user is puzzled, then maybe it can ask some good questions to lead the student out of the puzzlement. And if the computer thinks the user is bored, then it may tell a joke, right, to wake up the student. And if even the physical state, if the computer thinks the student is tired, then it may say, go to take a nap, come back in 2 hours. So emotion and cognitive state recognition could be very useful. So these two are from the human to the computer. Also, of course, the computer wants to convey information to the user. And in many applications of intelligent agent transaction with the user, it'll be nice to represent the agent by a talking head, synthetic talking head. So the person will be talking to a avatar instead of talking to a screen with some text and so forth. And one interesting and challenging issue is how can we implement the avatar which is emotive, which has expression. That is, depending on the situation, of course, once the agent decides what to say, so you have the text, and you use the text to drive the lip movement, and then you have synthesized speech. But depending on the context of the sentence, you also would like to synthesize expression, whether it should be happy or sad, and also you should try to make the tone of the voice expressive. And one of my students is working on that, and it turns out changing the expression of the avatar's face is not that difficult, although if you go to the details, there are some interesting challenges. It turns out to be much more difficult to synthesize expressive speech. All the commercial text-to-speech synthesizer gives you neutral, somewhat pleasant speech. But if you want the speech sound angry, fearful, and so forth, it's quite difficult. So my student is working on that. Then finally, we're interested in multimedia search and mining, especially search and mining of image and video data. Now, there are many issues here, but one of the holy grail, or the holy grail of multimedia or image and video search and mining is the so-called semantic gap. How do we bridge the semantic gap? Thing is, for searching text, we use keywords. When we search images for images and video, we also would like to use keywords. It's an easy way of doing the query. However, many of the large image and video databases are not labeled. So you just don't have the keywords, or you don't have the right keywords. So what do? Well, you would like to label these large databases. I mean, you can ask people to do it for you, but it's very expensive and tedious. So you would like to do it automatically. Now, from images and video, and also the audio part of the video, you can extract low-level features quite easily about color, texture, movement, and so forth. But you would like to map these low-level features to high-level concept.
Keywords. And the question is, how do we do it? Or is it possible? So one interesting approach we're exploring is, on the web, we have many tons of multimedia data. We have images surrounded by text. We have video with transcripts. So from that, we can mine that and try to come up with annotated database automatically. So one project we are exploring is, take Wikipedia. Wikipedia, each article, the title is sort of a keyword, a concept. And within each article, you have images, which are usually related to this keyword. So you can take each title and associate the images in that article with this keyword, using the title to label these images. Then we get a very large database, except the big challenge is, obviously, the database is not far from perfect. And for each title, many of the images may not be appropriate. So you need to prune it. And the question is, how do you prune it? We have a database of 24,000 keywords and 150 images. So each keyword has a number of images. So we would like to prune it. So we're taking volunteers. Anybody want to help, you're welcome.
But one possibility is, again, using the web scale interconnection. Try to make people who are connecting to the web to help you if you can design some clever ways. Yeah. Okay, so these are the 4 areas. Now, before I turn the podium to Mert and then Dennis, I guess since we are in the series of speed seminar, the burning question for each application is how fast is fast enough? In video processing, if we can speed up using GPU or whatever, what do we want? What do we need? And the answer for video processing is very easy. It's never enough. Okay. Now, the reason is, there are 2 reasons. One is the huge amount of video data, and the other is, in many applications, real time is not enough. Real time means 30 frames a second. Okay. But in many applications, you need much faster than real time. So I'll just give you a couple of examples. Surveillance, Chicago, we have about 4,000 cameras. Suppose you store 1 week's worth of video, 24 hours a day, for 1 week for all the cameras. You have about 700,000 hours, or 80 years of video. Now, if for some reason you want to search whether a particular person appears in any of the video, and you want to do it quick, you want to search it 1 week's worth of video in 1 hour, you cannot wait to find out. And it's not clear whether this can be done, but assuming it can be done. Yeah. So what you need is 700,000 times faster than real time. And if you think this is not big enough, think about the UK. They have 4.2 million cameras. So you have 700 million hours in 1 week. So if you want to search in 1 hour, you need 700 million times real time, assuming you know the algorithm. And you can look at other examples. For example, YouTube, as of August of last year, they have 140 million videos. Each one is about 1 to 10 minutes long. So it's about 12 million hours of video, or 80,000 years of video. So again, if you want to do things like you get a new video submitted, you want to search for near duplicates, whether you have something similar to it in your repertoire, and you want to do it quick, of course. You want it to do it in 1 hour, it's 12 million times. Now, however, we talk about speed up as if we know what to do. We only need speed up. Unfortunately, for computer vision, that's why I try to avoid computer vision, it's completely far from the truth. This is just for within this room. That is, in computer vision, most of the problems are unsolved. You don't know what to do. You can do a few things, but most of the problems are so difficult, you don't really have the right algorithm. So,
algorithm which works. But I think speed up could help, because if you have more speed, you can explore more possibilities. So in the long run, perhaps this use of speed up is more important than the first use. Just speed up algorithms which you know work. You try to use the speed up, the power of the speed up, to look into new algorithms. So to summarize, there are 2 things which speed up can help in video processing in particular. One is, if you have a working algorithm, you try to speed up to meet your requirement, such as real time. And the other is, for problems you don't have an algorithm for, hopefully the speed up will give you opportunities to explore more new possibilities. So what you'll hear next is 2 examples. One is from Mert on video event detection. And this, as you'll see, is an example where, well, for some event, you have reasonable algorithms. But for many video events, there are simply no good algorithms for solving it. I mean, the algorithms for detecting some of the events, many of the events in video, are so difficult
Nobody has algorithms which performs reasonably well. So this is the case where you can try to use speed up to help you to develop algorithm. And then in Dennis Lin's case, he's working on 3D hand tracking. Now, I hope this is true. Working algorithm is inside. Is it true? It's true, yeah, inside. No, not very far.
So graduation is inside.
Yeah, graduation is inside. Well, but slow, 3 years, right? Okay, but as Dennis will show you, he has an algorithm which sort of works, but it's not quite real time. Now, for human-computer interaction using gesture, we do need real time. And in real time is enough. Right? And right now, he can do it with GPU about, no, not quite half, 5 frames per second. Okay.
Okay, so these are the two different examples. One is speeding up algorithm which sort of works. The other is try to do things which we don't know how to do. So Mert will talk first, and then Dennis will talk. Okay, good. You can hear me, right? I can't hear myself. Good. So, I'm going to talk about our efforts for track with evaluation, which we participated in last year. So, track actually stands for Text Retrieval Conference, and it's been sponsored by NIST, and it's been going on since the early 90s. And it's, like the name says, it's a conference about text retrieval. And with the increase of multimedia content, they added a video track to it. And then that video track became so popular, it became its own workshop. It's a spin-off workshop. It's held at the same time with track, and it's called TrackWith. And what happens is they define a set of tasks, and they give you a certain data set. You apply your algorithms with the limitations of the task's definition, and then you compare your results every year at the workshop. So some of the example tasks are shot boundary detection, so detecting when the shot changes from one shot to another shot in, for example, broadcast video. It's copy detection, video search, summarization. High-level feature extraction is the task where you try to find semantically meaningful events in the video, such as they say airplane taking off, or there's a chair in the video. And the last one is the surveillance event detection, which we took part last year. And this year, with our collaborators from NEC Laboratories, we're going to try both of these, both high-level feature extraction and surveillance event detection. So what surveillance event detection is, they give you a video shot in a London airport, and then they want you to find all the instances of these 10 events. So those 10 events are somebody pointing just like this, or somebody putting their cell phone to the ear, 2 people embracing each other, someone taking pictures, someone running, multiple people meeting or multiple people breaking a meeting, opposing flow, so when you're walking into an area where it's exit only, and putting an object down, and if there's an elevator and the door opens but you don't enter it, they define it as person not entering the elevator. So let me show you. Actually, first I'm going to talk about what the data is. So it's, like I said, it's a surveillance footage from London Gatwick Airport. They have 5 stationary cameras, and the training set consists of 10 hours of video from each camera, so it's 50 hours. So is the testing set. Those are the same views and same cameras. The frame is kind of in the high to mid resolution range, so frame size is 700 by 500. And in total, that translates to 250 gigabytes of video that needs to be processed, and it's about 9 million frames. So you're looking for those 10 events in 9 million frames, in all those 9 million frames.
Question. So
yeah.
the training data set is labeled
Very good question. Training labels are only, they say, okay, from frame 5 to frame 10, there's someone pointing, without saying where someone is pointing. Yeah. So what we did was, we actually looked at a subset of those videos, and we actually labeled the locations of the people pointing also.
Manually?
Yeah, manual label. It was a lot of work. Yeah. So, let me show you an example video just to give you an idea. So here somebody put a cell phone to their ear. Here somebody is embracing up on the upper right corner. You can see them. It's quite difficult because there's lots of variation. Object put. So he put his luggage down. You can see the policemen are walking into a free shop where you're not supposed to walk in, only exit only. She was pointing, and this guy is going to take a picture. So up on the upper right corner. Yeah, has to take picture. And so you can see there are not too many motion cues, and there's lots of variability to the actions. So our system is quite simple. What we do is we get the video, and then we subtract the background. So we find the pixels that are where there's motion, and from those pixels we group them together to find regions where we look for regions where where someone might be performing these actions, and those regions are defined by the camera geometry. So from the labeled set of events, we know the camera geometry. We know approximately how tall the human is based on where in the frame he stands. So we look for lots of motion in the rectangles that are approximately the shape of a human, and then we deem them as candidate regions. So we take the window, and then we look in time. We extract the features from the candidate regions and also from the event samples that we have labeled. We compare them. Simply just we extract the features, some motion features that I'm going to talk about, and then we compare them. So now we have a bunch of and then we threshold that distance measurement. So now we have a bunch of points in 3D space, x, y, t space, which says here's this action or not. So then what we do is we cluster them together based on the intuition that if there are lots of flags in a certain area that says here's an action happening, then we say okay, there must be an action happening. Or if it's only one point that says there's an action, we just say okay, this is probably due to noise. So that's why we cluster the detections, and then we take the clusters with the highest membership, and then we deem them as detections. So, and then the most time we spent, the heaviest computation is spent by far in these two processes. So feature extraction and the pairwise distance measurement, as for obvious reasons. So how is our feature extractor? So yeah, question.
So I've heard that kind of comment before where someone says the phase X is dominant in this application, but then you speed up X by a factor of 10, and then other things become dominant.
Other things will become dominant.
So relatively, what fraction of the whole time is taken by those two phases?
I'm going to get to that in a couple of slides, and then we can discuss this in more detail.
Okay.
I have a slide about that. Yeah, so our feature extractor is Alexei Efros's work, which he did at Berkeley. So given a rectangular region in one frame, you look at the same region 30 from this frame and then the 30 frames after it, and then you define this video cube, sort of a video cube, as the patch where you're going to extract your motion features. So what you do is you subsample that video cube, and then you take consecutive frames at every k frames, at every n frames, sorry, by the definition of the slide here. And in our case, we look into 30 frames in time, so that corresponds to about 1 second for action, and it's reasonable because most of the actions, for example, pointing, take about 1 second. And then what we do is we subsample it by a factor of 5. So we have 6 frames. We have 6 frame pairs in time. So then what we do is we compute the optic flow from the pairs of frames. And optic flow gives you the displacement of pixels in 2 consecutive frames. So it's a vector image with 2 components, with displacement, and horizontal displacement and vertical displacement. And as we further break them apart into 4 channels, which is the positive horizontal displacement. So if somebody is going to right, for example, and then negative horizontal displacement if some pixel is going to the left. And then the same thing for the vertical part. And then we downsample those images as we use it as a dimension, as kind of reducing the number of pixels in those images, as well as a smoothing factor. So when we're downsampling, we're actually taking the mean and assigning it to a 1 pixel. And then once we have all those components, we just concatenate them as a big feature vector. So this is our feature vector for one patch. So how do you compare it to something else, for example? How do you know that this feature vector is actually coming from an event that you're looking for? So usually in a classification setting, what you have is positive samples and you have negative samples, and then you define a function based on the label information of these points. You define a function over this space, and then given a new point, you evaluate that function and find if it belongs to class A or class B. I'm talking about binary classification here. So one of the easiest things and you can do is the nearest neighbor, right? So given test points, which I've shown by stars here, you can find their nearest neighbor and then say they belong to the same class as their nearest neighbor. This is kind of one of the naivest approaches you can do, but if you tailor your distance metric carefully, it's also one of the most powerful. The problem with this one is it's very computationally time consuming. So you have to compare to every single training sample in your data set. So what we do is we say forget about the negative samples, because we have 9 million frames. So finding the negative samples that are relevant to your case is quite difficult in a video setting. So what we did was we took the naivest approach in this case and said, given a new test case, if there's a positive sample within a certain neighborhood, within a certain sphere of certain radius, close to my testing point, I'm going to say, okay, this is a detection. Otherwise, it's not. So one reason for doing that is there's lots of variability to the action. So it's kind of hard to learn a template classifier that will encapsulate all kinds of instantations of your action. The second one is, like I said, it's quite difficult to know what kind of event examples are relevant. And then the third one is this serves as a really good metric. So if your algorithm cannot beat this one, you should question your methods. So, and then we also have an ad hoc approach to detecting opposing flow. So we looked at, so the definition of opposing flow is if you see someone entering through these doors, either through these doors or these doors, you report it as opposing flow. We said, okay, this looks more like this looks easier, and we say we can probably solve it by matching it to a certain filter. So what we have is a Gabor filter, 3D Gabor filter, that kind of resembles a point or a pixel moving from right to left, and I'm playing the slices of this Gabor filter in time in this animation. So what we do is we define 2 regions for each door, here and here. We come up with this filter. We just come up with in time with this filter. We just do a 3D convolution operation, and then average those regions independently. Average the response of this filter in these regions independently, and then we look in time. So this is the you can think of this axis as time, and this one is the average frame response for one of these regions. And then we look at the peaks in this time axis, in this graph. And then if the peak corresponds to a motion from right to left motion, and when the door is open actually, then we say, okay, somebody walked in, and we deem that as the event detection. So this is the ad hoc approach, but this one also involves a 3D convolution, which is a pretty hefty operation. Oh, it's the other way. Okay. So as for the result, so this is for pointing event, yes. What we
this is a terrible result.
Yeah.
This is a difficult pointing. There are all kinds of ways of pointing.
So this one is with the naive system that I described, and our two runs are just are submitted by just choosing a different threshold for the clustering at the clustering stage. So you can see that there are about 2,000 reference events, and we managed to find about 10% of them in one of our runs, at the expense of finding 30,000 false positives. And this is the NIST metric. So the lower your score, the better. And they define this metric based on some
NIST has this
some weird metric,
which is actually not very good. But that's a metric they compare the different algorithms, and the smaller the better.
Yeah.
And
So
actually, one interesting thing is if you do nothing, you get 1.
Yeah.
None of these beat 1.
Yeah.
Yeah. These are all on the same data, or are these all running on different data? How many actual true positives are there?
About 2,300. So those are the reference events. And so we look at 50 hours of video.
So you're missing a lot.
Yeah. That's right.
The bad thing is the false alarm. There are too many false alarms.
Yeah, actually finding some of them is good. That means it's actually finding some. But you shouldn't give false alarm at every other frame. Right. No, actually.
9 million frames.
There are 9 million frames. So it's. I mean, I'm just exaggerating. Anyway.
So the best according to NIST metric is the
CMU. Oh no.
No, it's a
SJT.
Shanghai Jiaotong University.
Yeah.
So there's a student working on that, and he'll come to join us next fall. So hopefully we can raise the score.
Or lower.
If we can't beat them, we transfer their student. So that's nice.
You know if they're changing their metric?
Well, I don't know. Are they
No,
changing the metric?
no, the metric doesn't
They're not
change.
changing the metric?
No.
Well, then I think we know what win.
So it's just based on how important the false positives are in relative to the true positives. So okay, so for this one, it's a little bit more meaningful.
So this is actually a case where the results are reasonable. The best one in true vision, it's pretty good.
Yeah.
There are only 12 events, and they found 9 with 12 false alarms, which is reasonable.
Yeah, which is nice. And most of the false alarms are if someone is walking inside from right to left, so they just detect that person as if they walked in.
So you see the score is much lower than 1.
Yeah. So it's actually a meaningful metric for this kind of rare events, which only happens 12 times in 50 hours. But they kept the metric for some reason for the other events also. So yeah,
but unfortunately, most of the 10 events are difficult.
Oh yeah, they're very difficult, and they're very frequent too. Yeah. So we did fairly well in this comparison also.
What's the runtime? I guess it's more than real time. Right?
Oh, it's more than real time. It's more than real time. In fact, I think it was about, when we were processing, we were faring about 3 days per video. So 3 days for 2 hours of video. And since we were lucky enough to have the AC cluster at NCSA, we had access to 64 nodes. So we could run a bunch of jobs in parallel. And I managed to crash it once, the cluster. So, yeah. So, as I'm coming to your question now, so as of the timing spent for each component, so the feature extraction takes 37% of the time when we're purely CPU processing. And pairwise distance measurement, that classification part, or template matching part, is actually 61%. And everything else in this timing is negligible. Right. So, and we ported this same algorithm and we wrote it again in CUDA, and we ported those two components, so the feature extraction and pairwise distance measurement, to the GPU, and actually you get a significant speed up in terms of the total time, and also in terms of the time that each of those components spent. So right now, what's happening is the most of the time is spent on pairwise distance. This is right? No, this is not. Optical flow, right? Yeah, this is still on the CPU. The optical flow algorithm is still on the CPU. And most of our time is actually spent on detecting the finding the optic flow. And then the other one is decoding, and then just decoding the MPEG-2 sequence and then just changing it to a grayscale video. And you can see that feature extraction actually sped up quite a lot in this case. And we're also paying some overhead for transferring to GPU, but that turns out to be insignificant because if you look at the total timing, so the blue bars are GPU timing, the red bars are CPU timing, and this is a log scale. So if you look in comparison, that we get some pretty hefty speedups in the parts that are killing us in the general algorithm. So it's in total.
What is feature extraction?
Feature extraction is just computation of the patch descriptor.
After you get the optic flow.
Yeah, after the optic flow. Optic flow is here. So we spend same time because we do it both on the CPU in both platforms. So yeah, that's the. So as I said, by utilizing GPUs, we get some good speedups.
Is this against one CPU or is this against?
This one CPU and one GPU utilized in both cases. So we only run one core on the CPU and we only run one GPU when we're doing this comparison. Right? Yeah. Okay, so lastly, I'm going to advertise our computing platform that we're mainly building for the THuang this year, but we actually imagined it as a more general library of computer vision in video. So what we're doing is we're implementing a bunch of atomic operations that are necessary for this kind of video analysis in both C++ and CUDA. So what we have right now, what we have is the MPEG-2 decoder that we steal from OpenCV, and then we have a bunch of atomic operations that are good for THuang with algorithms. So for example, we have 3D convolution, which we use for the opposite flow detection, or the motion feature extraction and pairwise distance measurements. So these are quite general, and we have the CUDA implementations and C++ implementations, and also Python implementations. And the overall library is bound by Python, and it's very modular. So you can plug in, swap out different components. For example, this is the code flow of the THuang with video of our system and THuang with video processing. And so you can see we can define a bunch of objects for handling the video, so video input. And then we define the feature extractor here. This is the C++ version, and then this is the loop. When we loop over the frames, we extract the features. We do the pairwise distance measurement. And then going from C++ to CUDA is actually quite simple. We just use a different function, and it does and then we get the following speedups. So as you can see, we get about more than 100 times faster for feature extraction, whereas for the pairwise distance measurement, it's about 310 times faster.
Wait, where are you doing the distance?
Right here, this PW distance pairwise distance. So this is one matrix of features. So test features is the other matrix of training features, and then we just compare them one by one, the columns one by one, and we output another matrix.
So the distance includes squared and the square root?
Yeah.
No square root, just square.
Oh no square root, since we're just looking for the minimum, right?
So it's just the dot product.
Yeah, just dot product. No, not dot product. Euclidean distance.
And the multiply.
Euclidean distance.
Okay.
So
Yeah.
you're not using SPU kind of stuff either?
No.
We pull about 20 gigaflops with that on a GT200, which is a little sad, but it's kind of like makes it multiply.
Okay.
And this is a linear pass through all the data?
Yeah,
Or
this is
are you
one lane.
organizing the points?
There's little caching involved, as in for consecutive frames.
It's actually just a picture.
For consecutive frames, we don't reload the video, all those for 30 frames. We just load for the jump. So in this case, we just load one frame and swap out the other guy. in the front. So, but this one is averaged over multiple runs, so this should be quite accurate.
But you're doing a nearest neighbor search, right?
Yeah,
Are
yeah.
you doing any organization of the points that you're searching in, or it's just a...
No KD tree or anything like that, no. Just brute force nearest neighbor. So yeah, and if you're interested in, we're actually looking for people who would contribute to what we call the Vivid Library, Video Vision Library. So you can email us and we'll let you check out one copy from our Git repository and you can play around with it. So this is TrackWith. Thank you very much.
Okay, can everybody hear me? So how much time do we have left?
15 minutes.
15 minutes. Okay, that's yeah. Okay. How's this? Okay. Okay, so as Professor Huang said, I'm going to talk about vision-based hand tracking using GPUs. And generally, the idea here is that we have one or more cameras pointed at my hand, and we're going to try to estimate all the joint angles of each joint. Now, this is probably overkill for most applications, but in some sense, this is as much information as you can possibly extract. And in some sense, it's nice to be able to have everything and then do the analysis on that later. Now, once we do that, we can try to do things like analyze human kinematics, how people move their hands, maybe for psychological type studies, but also kind of interface applications where we want to have natural interfaces that let you communicate clearly with the computer. And they're also in, say, virtual reality or augmented reality cases where you don't want to have a input device to carry, you don't want to have to carry an interface device with you. And in some sense, this will be the first step towards sign language recognition, but that would involve tracking both hands and understanding facial expressions for a full understanding of, say, American Sign Language. So the difficulty in doing hand tracking is there's a couple of minor ones and then a major one on the next slide. The minor ones are the hand is a fast-moving object. The arm moves pretty quickly. I'm actually just going to completely ignore that and assume that the hand is roughly within the camera space and it's not moving too fast. But even then, you have huge muscles in your forearm moving tiny little masses in your fingertips. So you can do this really fast. This motion was actually faster than our data glove, which samples at 80 frames a second could detect. Also, the next thing is a lack of texture, which is both a curse and a minor blessing. The hand is, by the time you're looking at it on camera from about out here, you're not going to see much detail in the hand. It's going to basically look like a skin color blob. The silver lining here is that it's a skin color blob. So as opposed to tracking my arms, where you have to try and figure out what color my body is, and since we all wear clothing most of the time, you're never quite sure what color to expect and what texture to expect. For the hand, you actually do know that it is in fact a skin color blob, but the problem is there's nothing on there to track. So all you get is the overall shape. And the overall shape is tricky because you then get cases of occlusion. You can do very complicated things with your hands. Your fingers can occlude and cross themselves. And this can lead to fairly non-trivial kind of configurations. And the other problem with these hard configurations is that there is pattern in the space of all possible hand shapes. This is a hand shape, this is a hand shape. And if you look at all of them, there's patterns to them because you have segments linked by joints. The problem is that there are segments linked by joints, and jointed motion or articulated motion is very hard to characterize. If you have, say, if you're looking at, say, facial expression, you can take kind of two face images, kind of average them together, and you still kind of get a face image. There's some minor issues with that, but you can't do that at all with articulated motion. It's just not the way the space is structured. So you have to find some other way of characterizing the structure of this space. And this brings us to the actual very major issue with this. The actual space that you're dealing with is very large. So You have about 20 degrees of freedom in all the joints in your fingers. That's one hand. And then if you put the hand around, you have 6 degrees of global freedom where your wrist and your palms are oriented. To put this in perspective, the rest of your body, if you count all the other joints, has about 50 degrees of freedom. So if you take 20 multiplied by 2 for both hands, you're getting close to the rest of the body. So there's a lot of flexibility in your fingers. And this is, once you get beyond maybe 6 or 7 dimensions, it starts getting hard to use, say, a KD tree or other tree-based searches. So you're starting to really feel the cursive dimensionality. Now, we've done some work, and if you actually look at if you actually take samples of people actually moving their hands, you find that they don't actually occupy all 20 dimensions in some sense. They kind of lie on a lower dimensional. I don't want to really call it a manifold because it kind of crisscrosses back onto itself in a complicated fashion. A manifold is supposed to be smooth everywhere. And the problem here is that this thing is kind of really curved inside this high dimensional space, and it's kind of hard to characterize. So unless you can represent it really well, you're basically stuck with working in a high dimensional space. Similarly, if you look at hand shapes, there's all sorts of ways you can characterize. You got all sorts of length and all sorts of width and thickness, depth. We actually characterize the model that we use actually has 25 parameters. Locations of the base of the fingers, that's in X, Y. We assume that it's kind of planar in Z. And kind of the length of each of the phalanxes. We kind of assume that the girth is about the same for everyone. And again, if you take a look at this more carefully, you find that you don't really have 25 dimensions. You have more like maybe 5 to 8. But it's kind of, again, nestled in there in kind of a high dimensional fashion. Unless you have a really good idea of how to characterize that, you're basically stuck working with this. Of course, this being a research project, we actually don't have to worry about this. Is too much to try to do at once. So we take this approach where I just kind of I have this video sequence of my hand, and I've tuned it so that the model roughly looks like mine, and we go from there. So speaking of how we do this, we use what's known as an analysis by synthesis approach. We have camera images coming in, and we have candidate images that we're just going to render using our 3D model and our guesses at our model parameters. And then we compute the error of these two, so we get an idea of how far our candidate is from our camera image. And we use that error, we feed that error into the solver. Usually what we do is we take a bunch of candidates, and we compute all the errors, and we feed all those into the solver. And the solver comes up with more candidates to try. And we kind of cycle around in here until the error gets small enough, or we run out of time, and the next frame has come in. So this is roughly the system. We have cameras. We have 2 cameras, mainly to deal with the fact that we have complicated self-occlusions. One camera doesn't give you much. It doesn't quite give you enough information. And actually, if you had more cameras, it probably would be better. The cameras are presumed to be calibrated. And the thing we do, like I said, is we do skin color segmentation. Like I said, the one nice thing about doing hand detection is that you know what color they are. So the blue part here is not skin, and the reddest part is very likely to be skin color. We actually
we have 5 minutes.
Okay. We throw away everything except the shape, and then we use the distance function. I'm going to skip over the details, but the thing is that you have to use the chamfer distance, otherwise your results are horrible. And the problem is to compute the chamfer distance, what you do is when you have a polygon here, you want to basically compute the distance from the nearest polygon. And this is kind of blurry, but you can see how this goes from red to yellow, and this goes from red to yellow, and there's an intersection here. And if you do the if you're using 3D hardware, you can compute this directly by rendering extra things towards the back of the plane. This is kind of the Z buffer. So imagine normally your camera is looking here, and what you do is you render these yellow wings at the bottom of the Z buffer, and everything magically works out properly. So the advantage of using OpenGL to do this is that we are actually doing analysis, since we're actually trying to render the hand in order to compare. So we are doing rendering. So using OpenGL gives us the perspective camera and the polygon handling, and map-based zooming, all the niceties that you would expect, from a rendering platform. And we can play tricks with the hardware Z buffer, so that we can do things like the depth transform trick that I showed you. The problem here is that nobody really renders at greater than 1,000 frames a second, and I want, well, I guess I want tens of thousands, not hundreds of thousands of renderings at once. I can try to batch things together and try to throw large chunks of this at the OpenGL at once, and that seems to help. But other problem I run into, OpenGL is a black box. Usually what happens is that if you have a multi-million-dollar game, your OpenGL code just runs faster because the driver just makes it do that. And I don't have a multi-million-dollar game, so my code tends to run slower, and I have no idea when I'm running fast or running slow. And the other thing is that the way in some sense, my model is too simple. If you look at I have flat polygons with flat wings, very little texturing, very little shading, and this is not what OpenGL is designed for. And so in some sense, I'm basically bottlenecking myself writing to pixels to memory. So I ended up writing my own software renderer. And the software render is based on these little primitives, because I only have to render relatively simple geometries. What I call this little capsule. It's basically distance to the line segment, and I find a threshold. And within the threshold, it's inside. And outside the threshold, since we have computed, since the actual determination is distance to the line segment, we can compute precise distance transforms. And so we can compute both the hand and its distance transform fairly efficiently. And the main advantage of doing this is that when you write this in CUDA, you can avoid writing to memory. What you do is you invent, the CUDA system has what's known shared memory, which is a tiny little cache on the GPU die itself. And since I don't actually care about where the error is, I only care about the total of the error, what I can do is I can render the error into the cache, sum it up, and the only thing I have to ship out back into the main memory is the total. And that gives us a massive speed up, as you can see here. So this is number of comparisons a second, basically the number of renderings per second I can do. I've played around with this number. Sometimes it goes faster, sometimes it goes slower. I think I've hit as high as 10,000 on this. But I keep hitting bottlenecks with OpenGL, with trying to ship vertices down and trying to read stuff. Basically trying to ship vertices down and trying to structure things in a way that I'm not defeating all the hardware. And with the software renderer, I have with CUDA, I have a lot more control over what I'm doing, and I can get reasonably high speeds. If you work this out, I'm pulling about 80 gigaflops on a G92 hardware. So, and it runs about twice as fast on a GT200. So I'm getting reasonably good scaling, and this is so I'm getting reasonably good scaling, and I'm actually getting fairly good use of the hardware, although the algorithm probably could be improved. So tracking performance. I can track about half the speed. Now, Professor Huang said something, how it has to be real time. In some sense, real time isn't exactly frames per second, because it's also at 1,000 frames a second, there's no work to be done because nothing's changed from one frame to another. So it's all about how quickly you can adapt to the change that's happening. And right now, with a single GPU, I can do about half of this rate. And it does screw up a little bit towards the end, so I'm going to slide over into the next, to my conclusion. So having an accelerator and being able to do 25,000 evaluations a second actually does make a qualitative difference. I can sit on the command prompt, because this is all tied into a nice Python framework, and I can graph. So I spent part of last week, say, analyzing the gradients. And before, one way to compute the gradient is this finite difference. And if you can very quickly, say, evaluate 10,000 function evaluations, you can come up with accurate gradient estimates. And whereas before that would take a couple minutes, you kind of push go, and then you kind of go and browse the web for a little while. Now it basically comes back instantaneously, and the linear algebra you have to do afterwards is the bottleneck. It also makes it possible for me to explore large scale features of this space. Remember how I said earlier that hand gestures really isn't a manifold. It's kind of manifold in lots of places, but it kind of warps back to itself. And so if you look at the image space, it kind of does the same thing. You can have two different joint angle configurations that kind of end up with the same picture. They're kind of wormholes. And finding these is hard because it's a huge space. You don't really know a priori where they are. But if I can get on a cluster and evaluate millions of these per second, then I can go through and relatively, with some amount of pain, find these features inside this high-dimensional search space. Again, this is not a panacea. Amadeus law takes into effect, and every time.
Is this the right spelling?
I think so. I checked. I tried to check Wikipedia, but I could be wrong. Okay, so I don't know. Maybe that is not the spelling of Amadel, but did I misspell Amadel? Okay.
Maybe
DHL. Okay. Oh, maybe the H is in the wrong place. Okay. Okay. Sorry, Mr. Amadel. Amdal? That's probably why I spelled it wrong.
He's talking about a different law.
Oh. Thanks. And the other problem here is that I'm actually trying to build a real-time system. And so latency is an issue. There is shipping out and shipping back latency to and from the GPU. And it basically is leading me to put more and more of the algorithm on the GPU just to avoid that. And it also doesn't make the underlying problem easier. Like I said, I spent a bunch of time last week looking at how the gradients of this thing behave, and it behaves really poorly. You end up in kind of shadowish looking points all the time. So I'm probably going to have to reparameterize how, instead of parameters and joint angles, I have to say parameterize on points or something. And so in some sense, you still have to do research to actually get things to work. But it's kind of gratifying to get really nice speed ups on modern hardware. Okay, any questions or?
Yes, thank goodness. We have time for some questions.
Okay, so maybe let me ask
If
a
you wouldn't
question.
mind repeating questions, whoever answers
Yeah.
the question.
So maybe let me ask this way. There are two ways of looking at need for speed. One is to say, well, Dennis' thing is 5 frames per second now.
Correct.
So if I can make it 6 times faster, you're there, right?
Yes.
The other way is to say, well, Dennis' algorithm sucks. So even after we get to 30 frames per second, if we have faster computing power, we can get better algorithms and potentially more expensive ones. Do you have a sense of what is the additional that you really need?
Okay. The question is, there's two possibilities. One, since my algorithm currently runs at 5 frames a second, we want 30. If we can just get 6 times faster hardware, we'd be done. Or is there actually a fundamentally more difficult algorithmic issue that I need to tackle first?
You can repeat my question, right?
Huh? Is that the question?
No. You're right.
Okay. So the answer I have is, so on one hand, it may actually be easier than I stated. You may actually not need 6 times speed up to go from 5 frames to 30 frames a second, because as I said, as your frame rate increases, the amount of change between each frame becomes smaller. So it actually takes less effort to find the update. So on the other hand, latency issues become much more. So from a technological point, this becomes much harder because I can actually process things twice as fast on the newer GT200 hardware, but my overall algorithm, my overall program isn't running any faster because I think there's extra latency somewhere that I haven't quite tracked down yet. So it's not just a matter of simply faster hardware, unfortunately. Until everything's running on the GPU, I'm always going to have issues with transferring stuff. And on the algorithm side, I think the reason I ended up with the algorithm the way it is I tried a bunch of smart algorithms, and they all just didn't work. So I ended up with the dumbest algorithms that could possibly work. And that this is what ended up being implemented, and it works because it basically has to. I'm basically saying I'm going to throw tons of candidates at the camera image, and I'm going to pick the one that looks like the one that I have. If that doesn't work, then you're completely hopeless. So then I am certain that there is a better way to do this. I'm not sure if I'm going to be able to find it, though.
But I think you can do better by using more cameras.
Oh, yes.
3 cameras.
Yes, more cameras would definitely help. Yes.
You know, just sort of going along the same line here, couldn't you, I mean, hand gestures are not totally random.
Mm-hmm.
You know, I don't go from this to some other strange configuration.
Mm-hmm.
But there's a pattern in the gestures we use.
Mm-hmm.
So to me, it means couldn't you use some kind of probabilistic model?
Well, so on one hand, the answer, I mean, I prepared some extra slides just in case questions like this came up. But remember how I said that if we do the analysis, it's not actually filling the 20-dimensional space. It's actually filling more like 7 to 11 dimensions. Well, it's not exactly filling that either. See, this is what happens if we have people put on a data glove. And there are little red dots you can't see here, but there are 10 gestures that we said, OK, 1, 2, 3, 4, 5. And we asked them to go from one to another. And you can see that if it just fills in dimensions, you see just basically white noise. But there isn't. There is actually a structure in the way that people move their hands. And that's why we get these trails and places where things bunch up and places where things don't. Understanding this is also, unfortunately, really difficult. You need lots of fairly accurate data, especially if, and cross-modalities may be an issue because your camera is not perfectly calibrated to your glove and the glove slips. And so there's technical issues in trying to build an accurate enough hand model that it actually benefits the tracking. But in theory, you can definitely reduce the cost of your search. Instead of trying to search in a 20-dimensional space, searching in, say, a 7-dimensional space is exponentially easier. So if you can do that, then it will work well. But in some sense, we need to be able, the way I see this going forward, is that I would build a system which does the expensive search and use that to collect enough data, because then we can have enough, say, ground truth-ish looking data that we can build the underlying model and then use that to reduce the dimensionality of search. But you have to use the first one to bootstrap the second.
Yeah, that's interesting because the first one, you don't need to do it in real time.
I'm sorry. Yeah, I should have repeated the question, but
okay.
No. Question? Or no? Yes.
Does speed let you use general purpose algorithms as opposed to custom algorithms for video processing applications? So for example, for hand recognition, you have a set of algorithms. Similarly, for a different kind of recognition, you have a different set of algorithms. If you had enough speed, will it help you create a set of general purpose video processing libraries? So there'll be a library for recognition, and even though it may not be customized for hand recognition, it would not perform as well as custom hand recognition algorithms, maybe it would perform good enough.
Okay, so the question is, does having increased speed allow you to move from having specific tailored algorithms to more general algorithms? I think Mert might actually want to say something about this. I'd say for analysis by synthesis framework, that is a fairly general framework. It basically is you have some idea of what you want to looks like, and you just draw lots of possibilities until you find it matches what you see in your camera. So as long as you can render it, either using OpenGL or using some other simplified renderer, then you can try to do this. That said, there are technical issues involved, and trying to do it fast tends to run you into problems. Do you have any comment? Whether or not having more speed means lets you get away from specific tailored algorithms to more general algorithms.
So the way I'd like to, well, thank you. The way I'd like to use the speed as, so we know we have all these general algorithms, but we don't know actually what kind of parameterizations we want to run. So usually what you do is you try a bunch of different parameters. In video, that's really difficult. So you only have one shot to get it correctly. But if we have significant speed ups, we can actually try to really carefully engineer all these tools that we have such that we achieve the performance. So there's one thing to design the tool. There's the other one is to fine-tune the tool such that it, gets the performance desired. So that's the way I see it.
So I have a question for Mert. Yeah. Mert, now that we have GPUs for our use in TrackVid, do you think we're going to win?
So the question is, since we have GPUs at our disposal for TrackVid, are we going to win? It's participation that counts, right? But of course, I think we have a fairly good shot, and I'm designing a new algorithm this year. So it's going to be fairly complex, but at least we have a nice benchmark that we can compare to, and we can see where we're doing wrong. And certainly, since we have this cluster, we can rewind to a previous stage much faster, or we can tolerate some error in the design process. So I think we have a nice shot.
Can I see the slide where you compare what happens?
The problem with winning traffic is there's no cash prize. On the other hand,
how do you calculate the error?
So I skipped over the slide, but used what's called the chamfer distance. I'm sorry. Yeah, so the question is, how do we compute the error? And the error is, basically what you do is this is the camera image, the colored part. This is actually the error. The white part's the overlap, the blue part's a candidate. And what you do is you take, for each point in the camera image, you compute its nearest point in the candidate. And the reason you do this is so that the error goes downhill when you move the thumb towards the real position. Because if you move the thumb away, this here becomes a lot more expensive because it's far away from any blue pixel.
The error is the summation of errors.
Yes. But you can't just do pixel by pixel because the error points in the wrong way then.
Okay, guys, thank you very much. It was a very informative and fun talk. Thank you.